Next we have Grégoire Sergeant-Perthuis from talking about compositional statistical mechanics, entropy, and variational. Thank you.
So thank you very much for having me here. Very interested in this work. So some of you already saw part of it, like big part of the stuff in Cycle, so sorry about this one. There's some more slides at the end, but I do not have time to go on it. So most of the talk will be on compositional statistical mechanics, so I can introduce it, and then hopefully we'll have time to complete the rest. All right. So hopefully we'll have time to go to entropy, but probably not. So we'll see. Okay, so statistical mechanics. What is it? Motivations and problems. So maybe you're not, maybe you are or not familiar with statistical mechanics. But so what is it? Basically, you have a collection of random variables. Okay. And so collection of variables, for example, take lattice spin, you take each variable, take values between the -1 and 1, and you want to describe the correlations you have for, let's say, the dependency you have between the variables, and the way to do it is to put Hamiltonian so it's to introduce energy function. For example, here the Hamiltonian is the sum of the product of the different variables. So pair products of like two variables that are close to each other. So this is like the spin Ising model on a chain. And you're going to define a probability distribution using Boltzmann distribution, which is exponential minus beta h. If the energy is higher, the distribution, the state is less probable. So this has very strong relations with in computer science with Markov chains, hidden Markov models, graphical models, and they appear everywhere when you do Bayesian inference. So statistical mechanics and Bayesian inference and machine learning is basically the same thing. I mean, yeah, you could say this, or at least like random Markov field, but it's a big field of Bayesian inference. So in machine learning, it's called Bayesian inference, which is different from deep learning. It's not the same thing. Okay, anyways, so then what is the problem of interest in statistical microscopics? So basically, you have you want to describe macroscopic states of a system from microscopic description. And the thing is that what you realize is that matter can be for a given temperature in different states. And if you want to do it by, let's say, giving yourself collection of finite, like distribution of finite couples of variables, and you say that they need to be compatible by marginalization, you get a problem, which is that you don't get phases because Kolmogorov extension theorem tells you have only one. So then you need to find a way to define what is the notion of phase mathematically for an infinite size system. And so this is exactly what people try to do, De Bourchin, Ruel, and Ford. And they introduce a condition which tells you that you can define mathematically what the phase of a statistical system is. But now you have a big problem, which is that you define, so the real issue is that if you take an energy function and you sum over interactions on all the variables, it's not well defined. And even if you want to define it correctly, then you need to introduce some analysis, and it's still not very, it's still, let's say you still have a lot of limitation on what you can do. And especially most of the time you consider only translational invariant Hamiltonians, which is very restrictive. And so we have a problem, which is how do we relate Hamiltonians to phases? So the big problem is how to relate, how to characterize as phases from the Hamiltonian. And this is a very non-compositional, if you want to work with phases by changing the Hamiltonian, it's difficult because you don't control it. And you have, however, precise descriptions of how Hamiltonians are related to distribution through an optimization problem, which is called the variational principle, but it only works for invariant potential. And this is very important because this is where entropy will appear and free energy will appear. So that makes the connection with the end of my talk. But the problem is that the relation from energy to distributions is not compositional. And so one of the aim of the talk will be to make it more compositional. But first, let's try to go back and what is the definition of a phase in statistical mechanics. So like I said, you have a collection of random variables, so a collection of variables that take values in a state space E. We assume that it's finite here. And you're going to consider like the state of all the possible configurations of your variables, and then you're going to say that if you only observe like a finite number of random variables, at least this goes finite number of random variables, then if you have a finite collection inside of A, if B is inside of A, you have a projection from EA to EB. It's just you forget about some variables. So B is a collection of variables, A is a collection of variables, but you have more variables in A. So you have a relation between configuration from EA to EB. And this is just a morphism in the category of measurable spaces. So just to be clear so I use unconventional notations, but to be clear what categories I will be considering. So MES, which is the category of measurable spaces with morphisms, measurable maps. Kern, which is the category of measurable spaces with Markov kernels. It's not the same kern that the other consider, because it's not the same kern that's the other kern, because you don't have pointed distribution of the spaces. It's more stock, closer to stock. And in fact, I will be considering mostly finite measurable spaces because it's simpler this way. Okay, so how do you define the statistical system? So you cannot define it by the relation between the marginal distributions of the sub-collections of variables, but what you do is you assume that you have a zone in which you're going to experiment and you condition on what's around. So you force the values outside of the zone. So all these points corresponds to some variables, and you're going to force the values outside, and you're going to say, I'm going to give myself the information of how I can experiment, how I can observe things inside of this purple circle, condition on what's outside. So that's simply a probability kernel that goes from E and the complementary of A into E, and E being omega, so all the configurations. So you need a probability kernel, okay, and the probability kernel plays the role of a conditional expectation. But you have something more that you ask from this kernel, is that it has to be proper, which is basically saying that if I put if here, like I said, I was forcing what was happening around, what was happening in A bar. If I put an observable on A bar and a condition, it should not change what I'm observing on A bar. So if I do a measure on A bar, and then I look at what the conditional expectation I get from it, it should not change. So this, if you want to formalize it a bit more properly, so it's the notion of, if you want to formalize it more in the sense of property of the Markov kernel, you say that it's proper, which is basically if you go from a coarser, from a fine sigma algebra to a coarser one, you ask that the conditional expectation, like the probability kernel, sorry, that should play the role of conditional expectation, doesn't change your function. You have another condition, which is the chain rule, which is basically if I condition twice, I fall in the one that is with the less variables. Okay, so if I condition on A bar and then on B bar, it's directly the same thing like conditioning on B bar. So these are the two ingredients that are necessary to define more like an abstraction of what is a statistical system, which is a collection of conditional conditional expectations or conditional probabilities. But what plays the role of conditional expectations when you don't have a notion of, let's say, one global distribution, because recall that what you have is several distributions, then what you're going to need to have is a collection of Markov kernels that are proper and that verify the chain rule. Okay, and the Gibbs measure is simply a measure such that you get back the conditional expectation. When you take the conditional expectation, it is exactly the kernel that you start from. So Gibbs measures that are compatible with the statistical system being a collection of probability kernel, are simply the ones that are compatible with this probability kernel, which is that if I take the conditional expectation, I get the same thing. So in fact, yeah, like I said, this is really problematic, mostly because it's not compositional on the Hamiltonians. And so we'll try to make it, and also because you need to refer to a global state space, which is also very problematic because it implies a lot of analysis. And so we're going to try to forget about the global state space and simply redefine the notion of Gibbs measure locally without referencing at any time to a global state space omega on which all the variables live. And so the way to do it is first to remark that, so this was a specification, it's a collection of kernels. E is this global state space. These are the local observables. Let's say like C is a finite family, and the black lines are the kernels, and the dashed lines are the projections. Is to we see just a very simple remark is that you can extend this cone into a triangle, and then you can forget about the cone. So the first result is to say that a specification is completely determined by simply the action of the specification on the local variables. So the variables that depends only on the subset C, of this collection of sub-variables C. And then when you do this, you have this result, which tells you that you can extend it into a functor, and then you can forget. So you can replace specification by a functor, and you can forget about the state space, the global state space E. Okay, but that's it's not okay. So it's not that simple because when I do this, what happens is that I forget about the fact that the kernel has to be proper. So I need to also keep track of a seconds functor, which is the functor of observables, which is the ones that plays the roles of the projections here. So when I do this, the good thing is that I don't necessarily have to consider projections anymore. I can also consider any measurable map. So now the blue lines here are the traces of the Markov kernel on the local variables, and now the dashed lines go the other way around, and so you arrive to this definition, which is what is the more like at the say it's more topological definition of what a specification is. So specification being a statistical system is simply a couple of a functor, a contravariant functor, and a functor. One goes into the category of measurable spaces. One goes into the category of Markov kernels, such that one is section of the other. Okay. Okay. And now a Gibbs measure is simply something that is in the limit of the local of the functor of Markov kernels. So this is very easy to prove. So now we replaced, so in this formalism, we replaced a specification which was a cone with a couple of functor and contravariant functor, and the Gibbs measure is a limit. So you can forget about the state space and only work with diagrams inside of the category of Markov kernels and which have sections. Okay, so one thing that is interesting about this is that now you can start to do homology, like you can start to compute phases. I mean, so you can start to try to compute phases. You lose positivity when you do this, but at least you can have some information on the number of phases you have, which is by looking at the limit as an invariant and using homological algebra to compute it. One thing that is interesting is that if you want to compute resolutions, you can do it with projective objects, and you can characterize fully the projective objects of these Markov these specifications. So you have one result that is very non-trivial, which is that the projective objects are these ones. So that's normal. This is like something known for posets. But you can characterize them completing by saying that they are the ones such that the projections, the conditional expectations commute. And in fact, in the setting where the poset is the collection of finite sets of a given set, it's exactly equivalent to saying that you are looking at independent variables. So now you projective objects in the most restrictive setting where the poset is a collection of all finite sets in sets I of variables are exactly independent variables. So you can do resolutions in projective objects and in injective objects, and they are acyclic because they're projective. So just to give an example of what these objects are, if you take, for example, 3 vector spaces, like what is a projective object for a functor from a set from a poset to vect, it's you can see it as a. So here you have your poset 3 points. The posets, the enclosures go the way around, and each one has a vector space associated to it. This I wrote the vector space. This projection is the one that is just like a projection on each of the axes. This satisfies the fact that it can be decomposed. The projections can be decomposed as projections only on the subparts. So this object is projective, but if I change now the scale, the scalar product that I consider, and I redo the projection but with another scalar product, then you lose completely the fact that it's projective. And so this is something that's really important, because if you remember the first talk of yesterday, if you have martingales, you can see them as if you want to see them like seeing them in the Daguerre category is the same as seeing them as projections. And now if you have a big space from which you project, like you can see that changing the scalar product, it changes the projection, and changing the scalar product is exactly changing the probability distribution. Okay, so you can compute very small result from this is that you can also compute the phases directly of the projective presheaves. And okay, so this I skipped the result, but you have a complete description. And now what I'm more interested in is you can also have what is called something that's very interesting, which is extreme Gibbs measures. You can characterize extreme Gibbs measures. So in statistics, so let's go back on the results of what is extreme Gibbs measure. What are extreme Gibbs measures and probability? So the idea is you say that you have a system with an infinite number of random variables, but you want to find observables that depend basically, that are macroscopic observables on all these variables. Okay, and what you have is that your limits, like your phases or invariant measures for the specifications are the ones that they're entirely characterized by their effect, how they act on these microscopic observables. So this is something that's very important because you can characterize Gibbs measures, and also you can have something more that is even stronger, is that you can let's say characterize the extreme phases, so the pure phases, as being extreme points inside of the convex sets of phases in general. And you have this very strong property that tells you that basically, if you take two phases, they do not have the same support. They live on configurations that are disjoint. So you have all the phases of a statistical system correspond to a convex set, and the extreme points that you're going to get are the pure phases. And they also, so this distribution is on all the microscopic configuration, but you can characterize them only on the macroscopic configuration, and the macroscopic configuration is what is called the limits sigma algebra. So it's the intersection. If you take like the simple setting, we have a Markov chain, and I'm not saying so. There's always a okay. This is just a remark, but for Markov chains, there's always two ways of seeing it. Or you see it as a kernel, or you see it as a process. I'm seeing it as a process. If you can define the tail sigma algebra, this is where all the central limit theorem appears. This is exactly what I'm talking about when I'm talking about macroscopic observables. So the generalization of this result is, so yeah, I assume that positivity condition on the F being the diagram, so the functor that sends relations of the PO set to Markov kernels, assuming that they have a positivity condition, but I think I could do without. So you have that if you want to define the notion of tail sigma algebra, you have to define it locally also. So basically, the tail sigma algebra is defined as all the sets that are stable when you look at their preimage by the functor of observables. So the functor then goes in measurable spaces. Another way to see it is just if you see this as an indicator function, it's telling you that the A is inside of the limit of G. And this limit of G is also, yeah, okay, so it's in the limit of G. So this plays the role of the tail sigma algebra, and now you have the result, which tells you that you get exactly the same thing. And it's not that obvious to do. It seems trivial, like when you present it like this, but it's not. The generalization is not that obvious, at least for me. And you have the fact that extreme Gibbs measures are convex. That's okay. Then they're completely characterized when you restrict them to the limit of G or to like this tail sigma algebra, and you also have the decomposition, which is that they are extreme if and only if they are trivial on the tail. So this was not known, at least I don't think so, and not in this setting. Yeah. Oh, okay, so. And how much time do you have left? Okay, with questions? Okay. So yeah, I think this was not known, and I think it's interesting because it's one of it's a result that you obtain from reasoning locally, and it shows you that you can extend what was like classical results in this setting, and then from this setting you get more algebraic tools to tackle statistical systems. Okay, so now I was saying that there's a strong relation. So it echoes, of course, work that were presented yesterday, and from a group of people working on Markov chains and IID sequences and getting a categorical formulation of what is a law of large number, or at least let's say law of large number. And I would like to explore this more in detail. So what I was presenting here is in an archive paper, but now what if I want to talk a bit about entropy? So The problem when defining entropy locally, so it's statistical system, now we see it locally as a collection of random variables that have to interact through stochastic kernels, through Markov kernels. If you want to define the notion of entropy for the whole system, you need to start from entropy from local system, free energies from local system. And there's a very funny fact, which is that people have been considering these kind of structures in another setting, which is in the Bayesian inference on graphical models on the random Markov fields, and they came up with a very nice energy, which is called the beta free energy, which is not at all convex, which is a sum of like coefficients of the local free energy. So you can see it as a decentralized like cost function, but this quantity can be negative. So this is really problematic. This quantity accounts for not counting twice the free energy when you have compatibility. So if you have B, A, B, and they intersect on C, the CA allows you not to count twice C. And what you want to do if you want to have a variational principle is to minimize this free energy on Gibbs measures. And in fact, you can do it through a dynamic programming algorithm. And this makes the link with the second talk I will give this afternoon on how to optimize these quantities, in particular, how to use it in geometric machine learning, deep learning to be able to have more robust, efficient, like more capacity and effective modeling of statistical systems. Okay, thank you very much.
So now that you formalized this kind of system, getting away from the set of variables by just looking at the coset of Coponic, of what would have been Coponic, how do you expect to compose these things? If I have one of those and another one of those, do I do it by pushing out the cosets, or how do I put these systems together?
Yeah, you can. Yeah, I mean, you can. So these are just like. So the thing is that I never consider eclectic. So I see them as functors in vector spaces, basically. So you can always do geometric morphisms. So then you can always geometric morphism. You can go from A to B. You can change the basis, basically. And so which can be related to gluing things together, depending on how you define it. So another way, this would directly how to do it here is through resolutions, basically. Like you're going to have basically what you glued is already given by the coset. You don't need to glue together two cosets. You just need to define the system and then a good resolution so that you can compute the cohomology loops easily and fast. So I think the problem is to efficiently compute the cohomology loops more than gluing them together. I mean, like in the settings are already glued together by the definition of the coset. You can always change. So I don't know if it answers it. But you can change phases if you want to.
Maybe this is a little too far, but have you considered looking at this from the Markov category?
So, in what sense? Oh, yes. Okay, I understand. You mean generalize this, it have a result, but more not inside of this concrete category, but in the more general setting. Yeah, I would be very interested. I think it's possible because so it relates to the ergodic decomposition you have from that is known from Markov chains. And I think you can basically, if you take a diagram inside of the category of what you're talking about, then you could try to extend these results to also obtain like the limit filtration. I mean, you could. I think this constructions basically could be extended directly, but I'm not familiar enough with the more categorical formulation to do this myself alone.
I'm interested in how you start with thinking about subsets of the variables, but your cosets end up being the overlaps of the complements.
Yeah.
Yeah. Everything would. Can you say more about that?
So in fact, I hit it, but I forget. Now, after the good thing about this, I can forget completely about variables, a collection of variables. You just think about it as state space and morphism, which are measurable spaces, and kernels. So in this case, it's much more general than just looking at the overlapping. The second, I mean, one thing about your question is how do you handle infinity, or is it? It's not the question.
Not even particular. that also seems hard, but that wasn't why I was asking that.
Okay.
I just think this systems acting by what's going on with the complement of the variable. I think that might come up in other.
I mean, the problem is, the problem is that when you do the complement of something, means you have a whole set. And this is something you don't want because it's if you have a whole set, it's a lot of analysis, and even like for inference, it's exponential. The more you have variables, the more you consider them, the more it's exponentially costly to do inference. So if you break down the problem locally, then this notion of, I mean, so an answer could be you can put structure in your process. You can assume that it has semi-needs. Right, thing like this. In this case, you can recover, but the intersection. But the aim is really to keep it as a diagram, to have measurable maps, and to forget about the fact that it comes from concrete variables, so that you can have a really decentralized system on which you want to do statistical physics.
Right. Once you pass to the diagram and curve,
Yeah.
like what variable those objects came from becomes irrelevant.
Exactly. Then it's yeah.
If this requires a long answer, we can talk offline.
Okay.
What is the link with her? Is it really just mentioned?
So okay. So I'm not discussing the way you converge to. So I'm not converge the inverse Martingale convergence theorem. I'm just saying that when you have the limit. So basically, when you can decompose, to go to the limit is something something different. How to, so basically, are you asking how you converged, like, so there's this theorem for Gibbs measures also that tells you that if you start with any distribution, then you're going to converge almost surely for mu towards mu, and then if mu is in the faces. But the thing is that here I'm only talking about finite process and not looking at increasing process that are included in one another. This could be done, but this has to be done, so it's not obvious. And then, yeah.
They still have like a decomposition.
Sorry?
You still have like a decomposition.
Yeah, I have a decomposition, exactly. I have the decomposition, exactly. Yeah.
Okay, maybe let's talk about this offline. It's really interesting. Very good.
Thanks.
Thank you.